dt, so discrete number of variables, and we're taking them to be, just Gaussian distributed x1, and then the increments are Gaussian distributed, normal 0, 1, independent. So that now with this probability of x lying in a set A for all x and A is given by just this integral of the, product of PDFs, where F is the PDF of N01. So everybody knows this, right? And then the point is, if we take MT in the following form, see, this is the extension that we do in the Garzanov theorem. So it's summation mu I xi, and then this is this is basically, you can check, it's a strictly positive variable, and its mean is equal to 1, right? So whenever we have such a variable, we can use that to come up with a new probability measure. So that's the idea. So we'll have this new probability measure Q of A, right? So just bringing in M of T in this picture here, right, corresponds to expressing Q of A as product of, again, Gaussian densities, but now the Gaussian mean is N mu I1, right? So under this change of measure, the means have changed basically. So that's the idea. We've just reweighed everything. We looked at all these probabilities. We kind of, suppose your mu i's are positive, then we gave them a negative weight. We de-emphasize large values, we overemphasize small values, and then, oh, yeah. So under Q of A, that doesn't sound right, right?
Expectation on P.
Yeah, no, so under Q of A, the mean is minus of mu I. If you see here, this is actually a PDF of Gaussian density, but it's going to be e to the power minus x plus mu I square by 2. Minus mu I. Minus mu I, right?
X square into that UI square.
Yeah, yeah.
Then comes out as negative. If you're negative,
Yeah, I think this is correct, right? This is fine. It'll be minus, so this is, yeah, no. No, but this is a Gaussian with mean minus mu I.
yeah.
Yeah, that's what I'm saying. I made a mistake here. Because, I mean, I've de-emphasized large values, I've made the mean lower. So it's just clearly this. And this can be extended to allow mu i's to be functions of b1 to bi minus 1. So right now, I've assumed they're deterministic. I can allow them to be functions of this and still make everything work, which is what your Garzanov theorem is doing. It's sorry, F what? Empty is right, this guy right here.
Is there any reason couldn't play with the baby?
I mean, this makes it mean 1.
No, but you can also.
Oh, you mean here? Can we come? Yeah, of course. With discrete setting, you can.
Right.
With discrete setting, you can. With continuous setting, things go wrong. We won't be able to see it from here, but basically I mean, in some sense now, wherever the P of A has positive probability, Q of A might get 0 probability. So what goes wrong is a good question. Yeah, I don't have a. I think let's do this a little off. What your point is valid. You're saying, suppose I want to come up with a GI of X, whose mean is, let's say, minus mu I, but variance is, let's say, sigma square, or 2, let's say, right? Then what should MT be? So I think let's do this offline, because MT will not be such a straightforward expression. And then you have to ask yourself what happens to it as the number of t time, the time steps goes to infinity. And then you'll begin to see a clear pattern. It's a good effort to do. Yeah. Maybe next time I'll include it. Yeah. ठीक है, चलो, so let's now, so we did this last time as well, right? We discussed this multivariate calculus, so let me just review it. So B1 and B2 are independent Brownian motions. Whatever I say about B1, B2 holds for a multi-dimensional B1, B2 to BD. Okay, and then the point is the cross variation is going to be 0. And we don't exactly prove this here, we just give intuition for it. We say that this is distributed as T by N summation of UI, VI, where UI, VI mean 0 and independent variables. So by law of large numbers, this goes to 0, and hence this goes to 0.
We just for the sake of box calculus or something.
That's right, yeah.
Is this an infinity condition, meaning show the quadratic variation is zero, then it implies that they're independent as well?
If the quadratic variation goes to 0, no, that does not, right? It does not, yeah.
What does it mean?
I mean, for example, this B2 could have just finite variation, then of course it doesn't, yeah.
Both are Brownian motion.
Yeah, so your point is,
So we don't Gaussian covariance zero inside independent.
right.
Both that are
I see. So let's understand that.
yes, that shouldn't be.
Right. So the question is, if B1 and B2 were Brownian motions which were correlated, then this will not go to 0. So if it goes to 0, it must be independent. Yeah, I think that's correct. I mean, if they're both, I guess the way I was thinking about this was that B1, B2 need not be Brownian motions.
But given that structure,
Because I can construct B2 to be kind of, for example, yeah, I mean, something with finite variation plus Brownian motion. Uh, so then, and that finite variation could actually depend upon the other Brownian motion. So they're not independent anymore, but the quadratic variation is still 0.
so what is then what's the kind of definition of two processes being independent? Like, what does it mean for two processes?
I mean, I guess, so that's
Being happening
under their, I guess, for the two processes to be independent.
so does that mean for each time step xt, yt are independent variables?
Right. So we know the definition of two, I guess, the right way to, because, we define independence as independence of sigma algebras. So you'll have a sigma algebra associated with the complete process observed at the final time. So those two sigma algebras will have to be independent.
So the
That will ensure that sigma algebra will come. A probability measured on two sigma algebras.
yeah,
That's, yeah. So what are the sigma algebras? So I'm saying if process xt for small t going from 0 to big T and yt for small t going from 0 to big T, they're independent, then the sigma algebra corresponding to this process, which makes this whole process measurable, and those two
so some product algebra of x.
probability measured on that sigma algebra will be independent. Yeah. So that would be a precise
The
definition.
sigma alpha associated with the process is just union over sigma xt.
That's right. Because because it's a filtration, it just becomes the last sigma algebra.
No, but the filtration is the same across both xt, yt, right? That is, I mean,
So let me see. I guess what I'm trying to say is, just give me 1 second. So suppose I have this process xt.
what
So I have xt is measurable ft, right? And ft is subset of f, whatever, s greater than t. Then the sigma algebra I'm talking about is f of t, because it contains all the other sigma algebra.
yeah. So the second line belongs to.
It's measurable with respect to f of t. Yeah.
So I got this, but the thing is, when we talk about two stochastic processes, don't we need them to be on the same filtration? As in, like, if I just, because the filtration will be the same, right? From x.
So that's true. So in that sense,
Small sigma algebra is generated by the process. So that will be the sigma part. Yeah, so that will be sigma x sigma y.
yeah.
For t, these two will not always be FT. FT is they just have
Yeah, so they'll all be subsets of ft.
and these aren't necessarily increasing. And I mean, they are.
I mean, just by definition, they're increasing, right?
With the type T,
I mean, so, okay, FT depends on how you define FT, but suppose I define GT to be this, right?
yeah. Oh, it's up to
Up till time T. Then it becomes a filtration, right? Yeah. Yeah. So GT is with this, HT is the other guy, and then the 2 sigma probability measure. uh, Under probability measure P, the 2 sigma algebra are independent.
these two algebras are three independent.
Yeah, under a particular probability measure. That's right. That's right.
After the P that make them.
Under a particular P, they're independent. Under different P, they're not P. ठीक है. Hmm. Okay, so, but you got the point कि this being 0 does not mean that they're independent, right? This could be another um, another process of finite variation or finite variation plus some independent Brownian motion. And then also this will be true. Okay, so we'll denote it by this. And now we are just going to kind of state things because we kind of know how the proof is going to work. So we won't actually prove them. But let's take now ftxt. So we now have a general Ito process. It's a Ito process which is a function of it's a function of t as well as two Ito processes xt and yt. And again, whatever I'm saying for two Ito processes will extend to multiple Ito processes, deep Ito processes. So dxt is a1t dt, b11t db1t, so on and so forth. Right? b1t, b2t are independent Brownian motions. And all these guys are adapted processes. And what I really need from them is that all the integrals should be well defined. So one needs condition on them, but let's assume that's the case.
Okay, just whatever you need. B1 is B2 is fine.
Yeah, I'm assuming B1, B2 are independent. So in that world, I ask myself, okay, what's the Ito's lemma? That's Ito's identity satisfied by the function ft, xt, yt. Right? So it's very natural for now for us to expect it to look like this. I don't know what happened. Again, what you have in mind is you're going to take txt, yt minus f of 0, x0, y0, and then represent them in a telescopic sum, have Taylor series expansion, show that all the other terms, higher order are 0, second order terms stay in the game, and the box calculus basically holds.
Professor, we don't have like double differentiation with both respect to x and y.
No, we just have single differentiation. So you can show that f x square y, I mean f and double differentiation x and y is going to be 0. It's not going to contribute very much. So those things one has to show. So only terms of 2 degree remain. That will be 3 degree term. So that can be shown to be, because then you're multiplying by xt minus 1 the whole square and yt minus 1. That will still go to 0. Yeah, dbt. No. Let's see. No, we have this rule, right? Because they're independent. Okay, so far you understand, right? This should be the case. ft, xt, fx, dxt, fy, dyt. Now the question is, what's dxt.dxt? Anyone? What's dxt.dxt? This is your dxt, right?
B1 1, B1 2.
Just multiply this by itself, right?
B1 1 square B2.
Plus b12 square dt. Okay, that's exactly right. That'll be B21 squared dt plus B22. And what about dxt dy?
B21 square, B21, B11.
B11 times B21. Yeah. Right? That's exactly right. So this is clear to all. This is B11 square T B12 square. You can see box calculus at work, right? And now you can see you can do this over larger dimensions than 2. The dt terms always go to 0, yeah. Yeah.
So can you go to okay.
Okay. So when I do dxt dy db1t db1t becomes dt. And then these two get multiplied, yeah. Similarly from here, these two get multiplied. Okay. So now we know Ito's calculus in its generality. We have Ito's identity in its generality. Let's do a quick proof of Grasnov's theorem. We didn't do that last time. Okay, so recall that we have now this process, and with this process, basically with z of big T, we get a change of measure. And then, we had this E of zt given f of t is equal to small zt, z of small t. And that's given by this quantity right here. Okay. And the Grasnov's theorem was, so let's define b tilde t to be bt plus this drift, alpha t dt, this drift right here. Now, zt gives us a new probability measure, p tilde, given as follows. Yeah,
This is translation of the
yeah. Yeah, well, is it? Yeah, that's right, it's a translation of it, yeah. Okay, so under this, b tilde t is a standard Brownian motion, which means that under this change of measure, the old bt is now equal to standard Brownian motion minus a drift. Earlier it didn't have a drift, now it has a drift, right? Pardon, is this okay? So we need to prove this, right? We need to prove basically that this guy here is now standard Brownian motion under P tilde measure. Okay. And now we know that this is a continuous process. We know that its quadratic variation is dt, same as Brownian motion. We just need to show that it's a martingale under P tilde. And then by Levy's theorem, we'll have our result. Okay, so we just need to show it's a martingale. Now we know that, so to show the martingale, we need to show that this guy is equal to well, we'll have to show that, okay. What do we have to show? Anyway, we'll come back to that. We know that this quantity is true. I mean, I guess to show it a martingale, we need to show this, right? E P tilde B tilde T given f of s is equal to B tilde s, right? S less than T. That's what we need to show, but under P tilde. But we know that from P tilde, we can always go to P, the probability measure, right? And that's through this relationship. So this relationship allows us to go from P tilde to P, right? And what that means is that, it suffices for me to stay under probability measure P and show that this quantity is a martingale. Just stay at this for a while, right? Showing this property, because of this representation becomes equivalent to showing this property. Because this term here, the left-hand side is just E P Z T B tilde T given f of s upon z of s, right? So then showing this is equal to b tilde of s is same as showing this thing, this term right here.
So how did we go from y to b tilde as b tilde?
This is true for every y,
Okay.
for all y, for ft measurable y. So b tilde t is one example of that y. ठीक है?
This is less than t.
And s is less than t. Yeah. Yeah, s is less than t. Yeah. By the way, guys, this course was a little bit difficult for me to float because people thought we are covering too much material and it's too hard for the students here. Should not teach this. So if you can, if those of you who registered, just give reviews for this course. And I guess in some sense, your review is kind of suggesting whether this course should be taught or not. So that's, so it's useful as to what students think about it after having gone through the course. I mean, ideally, some of this material should be taught slowly in number of courses, but we don't have that option here. At undergraduate level, it's probably okay to get an overview, and then you're better prepared to do these courses in more depth later. Okay, so this is clear, right? What we want to show. Everybody with me on this? We have this property. We want to show this property. It corresponds to showing this property. Okay. So that's a nice relationship. So under P tilde showing,
But Prof,
Yeah.
the above properties for all y, and then we're trying to show it for just an instance of
no, because we just, I mean, our objective is just to show this, that B tilde T is a martingale,
of
right? We just want to show this for all TNS on all omega. So we use that property for a particular y equal to B tilde T. Okay. Okay, so earlier we had shown this. Do you remember this? That the ZT, the so-called likelihood ratio, the mean one variable, actually is a stochastic integral. It's a martingale and it's a stochastic integral. Well, should I just walk you through it again? Let's just do that. Huh? Should have it somewhere early on.
Yeah.
Yeah, so we took this, right? This is our ZT. We define the exponent as xt. Then ZT is just a function of e to process. Xt is given as follows, dxt is given as follows here. Then dzt is because it's e to power xt, right? So it's e to power xt dxt, and then again double derivative e to power xt dxt dot dxt. So you get this quantity, and you realize it's given by this following integral here. Okay. So it's already a martingale, but and it has this very specific form. Okay. Yeah. So we've earlier shown this. So now we just have to show that this quantity here is a stochastic integral. That's really the game, right? We show this a stochastic integral, we get that's a martingale. So this is just b tilde t dzt plus zt db tilde t. And now we understand this because we've done, this function of two Ito processes, db tilde t dzt, right? So this quantity from here, because we know what dzt is, we get this expression. B tilde t is nothing but dbt minus alpha t dt. And this quantity here just becomes, again, only the Brownian motion terms matter. So bt, you get alpha t zt dt. Yeah. Yeah. So you get this quantity right here. Well, this term right here, right? So which negative?
We have alpha t dt dt.
Uh,
There should be a negative term no? Because dzt is negative and dbt multiplied by this.
no, this is zt dt. Hold on. So this is zt. It's not this not coming here. This guy is exactly this term. There's no negative term here. Uh, I see what you mean. Mm-hmm.
I mean, we get DC from the DBT part,
Yeah,
but
yeah,
the lesser part is minus alpha TCP.
yeah. Hmm. Yeah, that should not be the case, right? So what went wrong?
Because otherwise we won't be able to cancel this.
No, I understand. Yeah. Hmm. Let me just reduce the clutter and see. Sorry. See, d b tilde t is this quantity, right? db tilde t is dbt plus alpha t dt, right? Hmm. And now you have zt is given, this is negative here for sure, right? This is not positive. This term was negative, right, in our earlier calculation? Let me check, huh? Because if it's positive, then you're okay. Hmm. Oh, sorry. Yeah, I guess this should be negative, right? So hold on.
I don't get the issue.
Yeah, so let's see, maybe I'm making a mistake, but at least this we understand that this is what we have here. Right, let's take this with us that dzt is given by the following quantity. Just wondering what happened. Is it fine? Yeah, maybe it is. Maybe I'm just chalo, so maybe I'm just getting confused. So we are here, right? ठीक है. So b tilde t dzt is c plus dt db tilde t plus dbt dct, right? And now this is, oh yeah, this is plus here. This is plus here.
Okay, then this was.
Yeah. So there was an issue. And now because db tilde t is dbt plus alpha t dt. And now this is negative. Yeah. Just remind me, I'll probably forget to change this later, but thanks. So then you're okay, right? So then you get your multiplier here. Okay. Okay. QED. It's not an intuitive proof, but nonetheless, it's what it is. We just show it's a martingale. Then that's then from Levy's theorem we have this very motion. It's still a yeah. I mean, this is still a plus because this plus comes from here.
T that T is
T
that T is still negative alpha T that T.
Yeah, that is still true. I just had made two mistakes, which were since the two rounds were making a right earlier. It does happen. Yeah. In the form which I showed you earlier. Yeah. That's it. We derived it, right? You just go back to that derivation. Only in that case, yeah, of course. Yeah. We constructed it to be a martingale. I mean, there should be a nicer way of kind of like we saw, in some sense, uh, in discrete setting we did see Gaznov's theorem, right? We did see this happen basically. Yeah. So that's kind of I mean, one can build a nicer intuitive argument from there. Yeah. So here just a proof. So this is a much harder result, which I will not even aim to prove. It's a demanding proof. But let me tell you what the result is. martingale representation theorem. So now I am restricting my sigma algebra to be this here. So all my noise in the system is coming only from the Brownian motion, nowhere else. That would affect the result otherwise. So if MT is a martingale defined on this space, then it's actually a stochastic integral. So every martingale, every continuous time martingale should be continuous time martingale, I should say that. Then there exists an adapted process BT such that MT is a stochastic integral. So basically every stochastic integral is a martingale, right, under conditions which we are not discussing. But now we're saying that every martingale is also a stochastic integral. Yeah, I think I'm being a little loose here. It should be every stochastic integral is a continuous martingale. But under basic filtration above, every continuous martingale is a stochastic integral.
Spaces,
Yeah,
but is there a bit more general or?
only for this, yeah. Because otherwise I can add other noise in my filtration and then you get a martingale from there, which is no longer a stochastic integral. But this is still a big result. Because in many, it's in financial world, you can assume, it's an assumption, of course, that all the noise is coming from the underlying Brownian motions. It's not coming from somewhere else. And then you can use this, yeah. So in that world, you can say concrete things.
Professor,
Right.
so if I have a filtration space one, and I have a second filtration space which has the same sigma f and measure, but the filtration itself is different. The two Brownian motion in this case would be different from Brownian motion in this case, right?
Just say again
So
the,
if I have like sigma TP is one measure space with some
Yeah.
filtration FT.
yeah, FTP.
Like the filtration is FT.
That's right, yeah.
And I have a second space where it's the same sigma, the same f, and the same measure, but a different filtration, let's say GT.
Yeah.
The Brownian motion processes in each space will be different.
I mean, it can be different. You'll have to construct a Brownian motion on this space, right? Now, what's the relationship between FT and GT?
There's no, like, suppose in general, if you don't know what they are.
So then you can do all kinds of things, right?
So in general, we can't say that the Brownian motion is the same in both spaces.
Yeah.
So then the question I have is, if the underlying Brownian motion are different in each space,
Yeah.
you're saying that you can replace the filtration with the one generated by the process. But then if you do that, they'll both come to the same measure space.
So I'll make so suppose, I mean, I guess the point is, I could have this space, right? On which I define this sequence of random variables, right? And I show that there are Brownian motion under this new filtration f of t, under this filtration of f of t. Then it will also be a Brownian motion under this filtration. Because this is going to be a subset of f of t, right? F of,
Yeah, so I got that. The thing is,
now if I have another filtration here, g of t, this process need not be measurable with respect to g of t, for example, right? So you run into all kinds of issues.
right, so I guess the only thing I'm pointing out is that in the definition of this Brownian motion filtration,
Mhm.
it implicitly depends on the previous filtration, like the underlying filtration. So, like in the notation that is doing that.
Yeah. So, I mean, all I can say is that if indeed I've defined this Brownian motion with respect to this filtration, then you can show there'll be a Brownian motion with respect to this filtration as well. Yeah, that would work. ठीक है. Okay, so this is going to be enormously useful. So this is again one of those big results, which one needs in math finance. One needs, it comes very naturally that this need, it was already there in this Brownian motion literature. So
Was it made for that?
it was not made for math. It just looked like it was made for math finance. It looked like it was made for math finance, but the result already exists.
Martingales were made for that.
No. Martingales also came earlier. Yeah.
But yeah, later on the other TD.
Yeah, I mean, they would finance some gambling examples were there for martingales.
Hmm.
Gambling example, not really kind of, this kind of finance. But for pricing options, this became very useful. And you'll see that right now. So let's come back to our two security model. Yeah. Calligraphic H square. Remember we started with this, we said that we'll define this integral f omega s dbs 0 to t for all f belonging to h of 2, which is all f such that f is adapted and and integral f square omega s ds in expected value is finite. So yeah, we are kind of not going into those details so much. Yeah. This how is drift coming here? Other constraint is just that the underlying filtration is this. That's it. Yeah. I mean, what I'm saying is, yeah, that we're not really talking about these things here. The integral is well defined. Okay, so let's come here. Yeah, of course. We always know that stochastic integral is a martingale. Other way around is also true. Just that if the filtration, all the noise is coming only from the Brownian motion, then other way around is also true.
But is that usually reasonable?
Well, when we did stock prices on binomial trees, we said the only noise is noise which stock price goes up, comes down.
No, but is that a reasonable assumption?
No. So I'm just telling you. So now that you have that point of view, you ask yourself, is it reasonable to assume in the world we are in that finance prices are, are the only noise that's coming to them is the underlying Brownian motion which makes them move.
Extending that, yes, but
Yeah. No, that's right. So I mean that kind of at least gives us a point of view to think of what's being assumed when we assume this, and what else could be there. So I mean, for example,
but I think it also depends on what you're modeling. Like if you're modeling finance over euros, then of course it's also subject to the same consequence.
I mean, you could imagine that in a better model is that there are other sources of noises, not just this Brownian motion. There are other Brownian motions or other processes, and that's determining a stock price. So then, I mean, if that's the real world, and now that's probably a fair thing to say.
I mean, when you look at very, very small time, like that,
Hmm.
then I think it's a good, because then you don't have a lot of other.
No, but we are making this not just for nanoseconds, right? Yeah. So it's a reasonable assumption. I mean, again, all the modeling efforts are going to be wrong, but it's reasonable in that sense.
Yeah, but I think his point is if we go like, I mean, all these modeling assumptions.
No, but option pricing would not make sense in nanoseconds at all.
Yeah. Yes. No, but when you go to the HFT world and then you try.
No, but we don't even use these ideas in HFT world.
Yeah.
So that's not the right world to look at option pricing. Yeah. Yeah. But you get the point that the real world is that the stock prices are being governed by all kinds of other processes. And you're assuming that's being governed only by one process. Yeah.
So why do we call this term geometric plumbing?
Hmm?
Why should we call this DST thing geometric plumbing?
I'll just come to it in a moment. Yeah. Where have we called it?
I mean, like I saw it in some other
So look, I'll tell you exactly when we use it. Because
yeah,
Because-
some other DS is equal to DS because S on both sides. So I think we can do this. Because how big without the multiplication of it.
I mean, when we take mu t to be a constant and sigma t to be a constant, which we'll do in the next slide, then you'll get that stock price is an exponential of Brownian motion. So in that sense, it's geometric.
This point is arithmetic without any multiplication.
It's because it becomes multiplicated because it's exponential of something. Yeah.
Like it's not addition.
Yeah.
It's because
That's right. That's right. That's the motivation for the name geometric. It's like geometric mean as opposed to arithmetic mean. Right. Okay. So we look at this world, stock price moves as follows. But now we are keeping things more general than before, right? Earlier, when we did Black-Scholes, we had mu t and sigma t as constants. We are allowing now to be adapted processes. And money market goes as follows, right? So m of t is just equal to m of 0 e to power 0 to t rs ts. So I'm allowing my short rate interest rate, instantaneous interest rate process R not to be fixed, but to be adapted process. Okay. So then this equation is going to be true. You can just check. dmt is rt mt dt. Okay. Stock price is given as follows. Now P tilde allows me to, basically come with a new probability measure under which dB tilde t is now a Brownian motion. So I choose a drift and I can twist I can change my Brownian motion by a drift alpha t dt, and under a new probability measure, it's still a Brownian motion. So I can do that, right? That much we know. Okay.
I choose any alpha t.
I can choose any alpha t I want. In reality, there are conditions of alpha t. For us, for example, suppose alpha t is bounded, then that's enough. Just Novikov is enough, yeah. Yeah, Novikov is a sufficient condition, but yeah, it's a good sufficient condition.
Oh, I thought that's the least.
You can do better than that too. It's a sufficient condition. But I mean, again, at the first order, we can choose a alpha t, and we can choose any alpha t we want. We haven't chosen. That's up to us. So what do we want to do? We want to choose a alpha t in such a manner that the stock price now increases at the same rate as the risk-free rate of return. Remember, that's the spirit. We want to make portfolios become martingales under some measure. So we'll choose a probability measure alpha t. So this is now a Brownian motion, right? I mean, so this is bt, I can write as dp tilde d minus alpha t dt. All this math that I'm doing with dt's and all that is actually rigorous. Huh? You can do the integral space. Everything goes verbatim, step by step. It's not like you're hiding something. It's just notation, basically, yeah. But it looks like we are doing more than just notation. Well, that's right. The discount process, this process will just increase at the same rate of return as risk-free rate of return. And then hence when we discount, it becomes a martingale. Okay, so this suggests immediately that I should choose my alpha t to be mu t minus rt by sigma t. So I have to assume that sigma t is positive always. Right? I'm not allowed to divide by 0. That's right, yeah. It's fair to assume that, yeah. Basically, if the noise becomes 0, then your stock price is not telling you what's going on with the Brownian motion, with the underlying noise. So you're missing out on something. Yeah, yeah. You can't infer the noise from the stock prices. That becomes an issue. Okay, so then you get this equation is true, right? So this is effectively what we want to use when we say that this is increasing at the rate as the same rate as risk-free security. The drifts are the same. And why this is important is because later we'll argue that ST discounted will be a martingale under this change of measure. Okay. Okay. So again, two security models. This is notes which I could have written differently. Yeah. Yeah, minus the na, so minus. Okay, yeah. All right. Okay, now I'm going to define discount rate, RT, this quantity right here. So, right. 1 rupee, well, how does one think about this? 1 rupee at time t. What is it discount to at time 0? Right? I need this much money at time 0 for it to become 1 rupee at time t. Hmm. Or RT is a discount rate. So now this will satisfy this equation.
Not even caring about the money market.
Well, it's the, I mean, RT is just 1 over my MOT, so discount rate is just 1 upon the money market. Yeah.
Exactly.
It's exactly the same. Yeah. Nothing has really changed. Yeah. But we want to look at this process, RTST. This is the discounted process, right? So DRTST is RT-DST plus ST-DRT plus DRT-DST. What's DRT-DST? Anyone? What's DRT-DST? Zero, right? Because DRT is a finite variation process. Is a finite variation process. Yeah. So you get RT into DST. So RT into DST and ST into DRT. And again, you get this representation here. I have just collected the terms with DT and with DBT separately. And again, when I choose my alpha t as before, mu t minus RT by sigma t, I will actually see cancellations. With this minus RT will exactly cancel with RT that I'm going to get. So I'll get the following relationship. So I'll see that the discounted stock price process is a martingale. Right? Alpha t I'm going to plug in as mu t minus RT by sigma t. Mu t will cancel here. RT will cancel this guy. Sigma t will cancel this guy, right? No. Yeah. I think the sigma t goes away. Just check for me. The sigma t is not there, right? It is there? Because, no, because it's here and it's here, right? In the denominator. Oh yeah, no, you're right. It's there. It's there. It's there. Yeah, it's there. It's there. You're right. You're right. Thanks. Yeah, it should not go away. I was wondering. But this term is coming. This term is coming from this term right here. So it stays. Other terms get cancelled. So everybody with me on this so far? Okay. Yeah, because both these terms get cancelled. Okay. And with this guy basically. Okay, so again, this change of measure is essentially this quantity right here is corresponding to this likelihood ratio or radon-nicotine derivative, where mu t is given as, well, this is what it is here. Right? Mu t is just the physical drift in the stock price. All right. Shall we carry on? Yes.
In the exponential of the t,
Mhm.
it should be the capital T, right? Not the tau.
Yeah, that's a typo. Sorry, this. Okay, so this is alpha t, just plugged in mu t minus RT by sigma t in place of alpha t. All right. The big picture is we quite easily found a change of measure under which the discounted stock price process was a martingale. Discounted risk-free security is just a constant, so it's also a martingale. So now a combination of these two will also be a martingale. So now let's start with the replicating portfolio process.
But how is it like?
Hmm.
Okay, martingale How does this help us? You see that?
Well, when you remember from discrete time, right? What we want to do is, yeah, that's right.
So earlier we had done what? Okay, earlier we said we match the coefficients like we did in the first case.
That's right.
But at the speed time also we then saw, okay, we think about the martingale and look at probabilities, and that's what we're replicating.
In discrete time, we considered a replicating portfolio process. We exactly replicated the option price and we said that's the price. Then we said, okay, a cool way of looking at things is let's come with a new probability measure under which risk-free and risky securities both are martingales. So any portfolio that combines them will also be a martingale. Right?
And then
Right. Right. And now the question is, can we construct a replicating portfolio process for the option price? If we can construct a replicating replicating self-financing portfolio process for the option price, then the option price process will also be a martingale, discounted option price process. That's where we're going with this.
and this new better come up with
Hmm.
equivalent martingale. Like,
Yeah. Anything you obtain by Gazanov theorem gives you equivalent martingale measure. Because all you're doing is you're multiplying ZT into a strictly positive Z2 to get the new measure. So both the sets give positive, same probability 1 to the same sets. Okay. Okay, so we start with this portfolio process, self-financing portfolio process. So if its value is xt at time t, and AT is invested in the risky security, then xt minus AT, nothing is coming in, nothing is going out. So the remaining wealth is invested in the risk-free security. That's why it's a risk. It's a self-financing process.
how we define
ST is the same what we had, right? We have this risky security here. That's how we start. So we are living in a world where we have a risky security and a risk-free security. And now we are just combining the two. Okay. Our levers are, total amount of money remains the same. If we invest AT in the risky security at time t, then XT minus AT is invested in the risk-free security. Yeah. Is it? Yeah. In this case, yeah. Because we have an exact form for it, right? I mean, it's exactly obtained by this Z of t, right? Yeah, so how do you define a probability measure? It should give the same probability to each and every set. Yeah. Yeah. Okay. All right. So we are here now. So that's our portfolio process. Now we are going to look at the discounted portfolio process. RT dxt, xt drt plus drt dxt. Again, this term will vanish because drt has finite variation. RT dxt is exactly this quantity, and xt drt is exactly this quantity. Okay. So you should be able to see that this term is getting cancelled, right? So you're left with these two terms. I take AT common, then you're left with RT dst plus minus, and this is just ST drt basically. So it's AT drt dst, and we already found that drt st has this following representation. So all this is saying is that the portfolio process remains a martingale, the discounted portfolio process. Yeah.
So XT is a linear combination of ST and RT.
Yeah,
So to conclude that the discarded process of martingale is not enough to say that RTXT therefore controlling the problem.
I guess so. Yeah, but it's good to show precisely. Yeah, it's actually a stochastic integral. So this is a martingale. So now we want to come up with a replicating portfolio process, which replicates exactly the option. Right now, what have we achieved? We've just achieved that there's a new measure under which any discarded portfolio process is a martingale, under new measure. What we'll do is we'll take option price V of t. See, option price, these are European options. So they just give a payoff finally. That's what we're trying to price right now. And it's basically payoff is just a random variable, which is a function, function of f of t at final time. What that means is it can be completely path dependent. Random variable, it's just ft measurable. So it can depend on the complete path till time big T. But we want to price this option now. So we are doing we're pricing much more general options now than before in our Black-Scholes example. And our underlying process is also much more general. It's mu t and sigma t, which are adapted processes. Okay. What we do is we just define, because we want Vt of Rt to be a martingale under P tilde. We just want it to be that way. We want the option price process to be this. So we define Vt as follows. P tilde is well defined. This conditional expectation is well defined. I can divide by Rt and can define Vt. So now my Vt Rt is a martingale under P tilde. So this is important, huh? So by martingale representation theorem, that's where it comes in. It has the following representation. I mean, the way to think about this is that this is just going to be equal to E P tilde e to the power minus small t to big T Rs Ts.
Minus is not sure, right? Because RT was minus already. So one minus.
Yeah, just think about this. This is integral from 0 to big T. This is integral from 0 to small t. So what's left is integral from small t to big T. Right? So now you're discounting up till time small t. That's where the martingale is. Yeah, yeah. Under that measure, option price is martingale. Okay. So we want to. That's what we think. That's right. So we are assuming that. Whenever we say martingale representation theorem, I should mention it, that Ft is equal to
So now, if we like D or B till now, like sigma.
right. That's a good point, actually. Yeah. Turns out you can show that they're the same. Huh? Yeah. Well, the question was different being asked. You're looking for independence at that time. Now we're saying they have the same sigma algebra. It no need not be deterministic, right? That's the whole thing.
No, the alpha.
Alpha t is. I mean, alpha t can depend upon Bt.
Yeah, but only in the past. Right?
Only up till the past. Yeah. No, that's right. I mean, it takes away the independence. I mean, his point.
You say, let's look at how B delta T is created. I'm looking at all the now it's still time T and that's enough. Yes, the group B delta T, I think to all the nodes till time T for
Yeah.
BT.
Yeah.
Because that also gives me the integral I've added plus subtracted.
I see. So,
So, you don't need
what point are we making here?
I think it's good.
Oh, okay. Now that's a different point. What he was bringing to was some other point. You're talking about independence. Okay. So let's keep that aside. Let's come to your point why they're equivalent. That we agree completely. Yeah, that's my point as well that they're equivalent. Although I'm not argue that fully, but that's a good point. Yeah.
It's just a deterministic.
Huh?
It's just a deterministic term of it.
Adapted term away from BT. Yeah.
Yeah, so yeah.
But the information in B tilde S is same as the information in BS. If I give you one path, you can construct the other path. Yeah. That was Rushil's point also. Yeah. ठीक है. So now we can apply martingale representation theorem and we can express this as follows. What shall we do now? Okay, in some sense, this is a conjecture for what the option price should be, right? V of t. It's not the option price right now. It becomes the option price if we have a replicating portfolio which finally replicates our option V of big T. And the option price itself and the portfolio value at time small t is given by V of t. That's what we want to show, right? So that sounds like a tall order, but it's actually quite straightforward. What you do is, we have this equation above, and we have this equation for any portfolio process. And any portfolio process, we really just have to choose A of t. When we choose a process A of t, the investment in the risk-free security follows, right? So I choose my A of t to be gamma t by RT sigma t st. Then that both the equations become equal, right? At every time on every sample path.
This is equivalent to the coefficient matching thing that we.
Yeah. See, because you gave me V of big T to begin with, right? That's how we started. You said, I want to price this option. So you gave me this. And we came up with a P tilde change of measure, right? From the underlying processes, we came with a change of measure under which stock price was increasing at risk-free rate. Under that, I defined this random variable V of T. So I defined this process VTRT and it's a martingale. Now, because we're on this nice space, this process happens to have this representation, gamma UTU. So if I can just come up with a replicating process which matches gamma U on every U, on every omega, I'm done. Then I've replicated this option basically. So earlier the problem which seemed complicated in discrete setting is easier in this setting. I just choose my AT in the following manner. So I construct a portfolio where every time the amount of risky security I purchase is just gamma T upon RT sigma T ST. Then both of these are equal. And in particular, and I also choose x0 to be equal to v0. I start with wealth, which is v0. I know what v0 is. So if I start with v0 wealth, if I choose my 18 in the following manner, one can show, but you can see by that be very plausible, that x of t is going to be equal to v of t. So I always wonder, both of these guys are writing at the same time. Is it the same notes or some other class notes? Huh? Or you guys are seeing each other's notes?
Probably it's just like, I ask the question later, I'll ask the same.
Okay, my question to you guys is, are you doing like some humanities course right now? No. I mean, you're not working on something else right now when you look at the class.
It's a lot of math, bro.
Okay, okay. I thought you're finding this too easy, you're getting bored and okay, all right. I'm thinking, okay, they're like time बहुत slow चल रहा है. Okay, guys, huh?
The question is, sure, we can do this theoretically.
Hmm.
How do we know gamma t? Because the market
That's right.
representation doesn't exist to gamma.
That's right.
How do we get gamma?
That's right. So it's a great point that martingale representation only shows you existence. It doesn't show you it doesn't construct it for you.
Quadratic variation. Like martingale itself has a quadratic variation. If you know, can be written in terms of the right hand side.
Yeah.
Quadratic variation on both sides.
That's an interesting idea, I guess. Yeah. So you can approximate the quadratic variation of the process, and that can kind of give you an approximation for this. Yeah.
No, but that's very specific in this case. But
That's a genetic thing. That's a genetic result. Because we know that for any martingale, what the quadratic, if it has this form, what the quadratic equation is going to be. But I don't know if that's how people do these things at all. I mean, for our kind of options, one just has a very exact formula for this. You can, the delta hedging, basically. Yeah. Remember, gamma t was what we had derived earlier. It was just option price that we had. At that time, we called it C of t, I guess. Del t by del S of t, I guess. Yeah. Yeah. So this was indeed this was your A of t, basically. Yeah. So from A of t, you can infer the gamma t.
No, but the point is we got this other mathematics in here. So you didn't know that. We know that
Hmm.
that AT should be del CT, del ST because
That we did all that. That's right. So yeah, so right now I don't have, so yeah, because that's in a very specific assumptions, right? We assume mu is constant, sigma is constant. Yeah, it's a much simpler world that we are in. And we are pricing an option which depends only on the final value. See, right now your V of t is a path dependent option.
yeah.
It depends on the complete, so all the stock prices up till that time. That's the way to think about V of t. It's a function of all.
The option price is not.
No. I'm saying you could have options like that too. Yeah. But when we derived it, our option price, our V of t was just this. So because of that simple structure, we could find the delta hedging, the A of t.
So as when you said this is the European option, the point was to say that it's you only know the time,
Hmm.
but the value that we take it whatever
Yeah,
whatever path that we're printing it.
that's right. It can,
That T measure.
yeah, it's a function of ST. So you allow complete generality.
And then you start with this.
Yeah. So then you have to worry about how to find the delta hedge. What the right hedging strategy is.
There's no general form of gamma T that we know.
Yeah. In generality, we don't know. Okay. So RT XT is equal to VT, RT VT, so XT is equal to VT. So in particular, X big T is equal to V of big T. So we replicated the whole option. Okay. And in particular, the price of the option now VT, well, price of the option which is XT is actually equal to VT. Right? Because the price of the option is price of the replicating portfolio, and that's equal to XT, and that happens to be equal to VT.
So I have a question.
Mhm.
If equalities in XT and VT is almost surely on the sort of trajectories that we have.
Yeah.
So it's maybe
XT and VT, it's path by path, yeah.
So there could be a certain measure zero on which they differ. So in the real world, if this is implemented, I mean, if you transpose that omega, your entire thing is.
Yeah, so with probability measure 0, you're going to really suffer. A lot of people can live with that.
I mean, higher probability that you're back to the
Yeah. I mean, in reality, you have discretizations, and then the world doesn't follow this model, and there are all these transaction costs. So all these are just guidelines. So if you're a trader, you're comforted that the option price from your mathematics is coming out to be 1.2. So you're happy selling it for 1.5. You feel, okay, you've not been cheated. So you have an idea of how much you can live with.
But also, where is option pricing like say used nowadays? Because other exotic options are mostly option prices are marketed,
Uh,
like determined by the market.
yeah, but so this theory then tells you how to hedge them. Prices are given by the market, but the hedging, so now I have 500 such all kinds of options. How do I hedge them together? So I look at their sensitivity to various factors. And then also, if I want to close my risk, I need to take a kind of counter positions to balance my, to hedge my portfolio. So that's where all this becomes very useful.
So my point is now, see, that in the case where the bank is writing an option or then you want the bank was which are more.
I mean, suppose you're an investor, you have 20 options and you're worried about their risk and you want to invest in the securities in just the right amount to capture that risk. Even there is, that's right, yeah. Well, but I don't have any risk. When you bought an option, maybe not with the speculative motive, but maybe with a kind of insurance motive. Yeah. But you want to cancel the risk. You worry about the risk a lot. So is this kind of clear? So it's a very clean theory, right? Now and as I must have said many times earlier, in the world of finance, once you can price something, then it's much easier for the market to be made. Then you have then easy for the buyers to find sellers and all of that. Because everybody's comfortable that they know what the right price is. Okay, so now let's come back to the Black-Scholes derivation. So our mu t is equal to mu, our sigma t is equal to sigma, and our t is equal to r in that world, right? Then our dst is given by the following formula.
These variations are not time.
No, they're constant. You always want to start with the most parsimonious model. So in small time periods, assuming risk-free instantaneous rate of return is constant is very reasonable. And mu and sigma, okay, not so bad assumption. So that's how it all started. And then your ST has the following form. You can just differentiate this ST and just apply Ito's lemma to it. And you get this result. We've done this already in more generality. But you see that now it's a geometric Brownian motion. Is this kind of clear? It's exponential of Brownian motion. Because this is just a particular Brownian motion with a certain drift and then with certain diffusive term. Okay. Okay. Now you want to know what this stock price process looks like under the risk-free measure, right? So you can see under the P tilde measure, the risk neutral measure. Yeah. Oh yeah. So under the risk neutral measure, we also call P tilde risk neutral measure because your security is moving at the same rate as risk-free security. So DST has the following representation, and it immediately follows that you get another representation for stock price. Okay.
Also, equivalent martingale measure and risk neutral measure are equivalent.
I mean, equivalent, yeah, because it's a unique martingale measure. So it's a measure under which the discounted process becomes a martingale. Yeah, so that's the same process where the risky securities grow at a risk neutral rate, risk-free rate. Yeah.
Yes, sir.
Mm-hmm.
So in the binomial kind of model we did,
Mm-hmm.
the underlying probability actually didn't matter at all.
So mu did not matter here.
Mu did not matter.
Mu does not matter here. Did I not? I should have mentioned this earlier. Let's go back to our. So our AT just depends upon RT, sigma T, ST, right? But mu shows up nowhere in this equation.
But in the binomial case, even the sort of the underlying probabilities, which are different from UT. I mean, the underlying probabilities are more analogous to the measure.
No. That's the thing.
Or they're analogous to UT.
Yeah. They give you the drift. The tree itself corresponds to sigma T. It tells you the paths that the option price can take. Yeah, that's interesting. So the tree has to be the same under the two measures. So that's why they remain equivalent. So now you can see, so where are we? Yeah. So we want to price the call option, right? So CTST is V of T, option price, and that's given by just the stock price S of big T, which has the following representation, because BT minus B tilde T is just normal 0, 1 in distribution times square root of T minus T, right? So this is sigma times square root of T minus T and 0, 1. This quantity should be R here, sorry, this should be R here. This should also be R here. Okay. But the point is this calculation you can do now.
Made us do this.
When was this in that other course?
Yeah.
Oh, is that right? I see. Okay.
You split by strong.
Oh, I see. Okay. I didn't realize that. I thought it was. Huh. No, but you should do calculations. Yeah, come on. No, but in some sense, if you do calculations, then you remember better. Okay, so this is how market prices options basically. This is how your calculator would price that. And the big thing, the way it's actually used a lot, and this is important aside, that option price is something that you know. So this C here, let's call it CT. And you basically infer the sigma which gives this price. So you infer the sigma. So in the market tells you what the price is. And R you can accept. K R is also very reasonable, you have a guess for it. You infer your implied volatility sigma. Implied volatility. Huh. I mean, in the sense, it's not even that you're inferring the Brownian motion per se.
No, but you try to approximate.
But I'll tell you the spirit in this. The spirit is that the option price is a monotone function of volatility. I think that's true. Yeah, no, that's true. Yeah. It's a monotone function of volatility. So then implied volatility becomes a proxy for the stock price. But now the point is this. Huh? It becomes, yeah, option price, yeah. It becomes a proxy. But the other thing is, that the real world doesn't follow Brownian motion, doesn't follow this Black-Scholes framework. If it was following the Black-Scholes framework, your implied volatility would be constant. Always. But in some sense, you have a sense of what the underlying model is by having a sense of how the implied volatilities behave.
So at different times and different sigma T's that are observed. That's what it is.
That's right, yeah.
But then how is that giving me anything, because that's directly violating everything I've heard.
That's right. So the real world does not follow Black-Scholes.
I agree.
But you kind of have a feel for, okay, so from this you can construct, from the option prices, you can construct the implied volatility surface.
What does that tell you?
That tells you that this is where the prices are currently. And you,
So, but you already know the price.
that's right. So it gives you a good way to interpolate prices, etc. You interpolate on the space of implied volatility.
So just to be sure, we say we built a model lab.
Hmm.
And now we see that, okay, sigma is not bound, which is a fair, but we needed this adaptation together. Now we see, okay, you observe something.
Yeah.
So some different prices at different times.
Hmm.
Based on that, I get some sigma.
I mean, you say that I'm not naive anymore, so I don't trust the Black-Scholes model.
But I still use it to somehow understand sigma.
Yeah.
And then try to extrapolate.
So Black-Scholes model is just an interpolation tool. There's no reality to it. Just it gives a mapping of price to implied volatility. Now, implied volatility in certain markets will be a smile. It's high on one side, it comes down, it decreases again. In certain volatilities, it'll be a smirk. So you have a sense of where the world is, depending on what shape these things are. So traders have an intuition for this kind of stuff. That's right, just an interpolation tool. And then you have a very good sense of how these things work.
Is there another tool to calculate implied volatility or just this?
Just this tool. It's standardized in this manner. Yeah. So everyone we don't quote prices, we quote implied vols sometimes. Traders would do that. This was 80s, 90s. But I want to say more, I'll have to brush up a bit. I'm not, this stuff I've been far away for a while. But you could read up maybe in John C. Hull and such books. on kind of implied walls and different types of things. Uh, but basically, you have a sense that if my actual process stock price is fat-tailed, then how will implied volatility look like? So, so a lot of intuition is kind of comes up from the shape of implied walls. So, is there a question here? K is the strike price of the call. So call option has a strike price, right? I can purchase the option, I can purchase the stock 3 months later at this price. That's what the option buy is.
The current price, like after 3 months.
Yeah, that's right. Current price is this. After 3 months, it'll be this random variable. I'm allowed to purchase it for this. I'll do this if this is positive. But the price of the option turns out to be under this change of measure.
But somehow factor in the price of the call price into an option. Or
Yeah, when we make,
not in the payoff.
we kind of in the payoff, we do that, right? We say at the end, depending on the stock price, this is the payoff we get, right, for the option.
Allowance
You know, KST. But our profits are a function of, okay, we also pay some price. Yeah, that comes in. But what's the right price? That now we have a theory to find what the right price is. We didn't have this earlier. And right price is, what's nice about all of this is it's not really that theoretical. Because right price is exactly the amount of money you need to hedge against that risk. That's the amount of money you can create a replicating portfolio. So whatever risk you're exposed to by selling the option, you can exactly match it. So it's very kind of practical in that sense, this price. Okay, yeah, so what else do I want? That's right.
You can use sigma to get fat data.
Huh. So we'll discuss this.
We saw fat data would involve jumps.
That could be one model for it, sure.
But now
Yeah.
the thing is here you just have Brownian motion.
That's right. So we didn't use any of that. So we use a nice model of the world.
Just like no key.
No, I understand. Just complete the story. Yeah. We just assume that DST is DST by ST is mu dt plus sigma dBt. It's a very nice world to assume, right? All the changes are happening because of Brownian motion. It gives you certain option prices. After, as I must have mentioned earlier, after the 1987 crash, before 1987 crash, Black-Scholes fitted very nicely to all the option prices. Your implied volatility remained constant. And that's because everybody on all sides was using the same formula to price things. They use the same formula, so they will get the same results. But 1987 crash happened when they lost 23% of market value on a single day. And then they realized that stock prices don't really follow this nice Gaussian process. They have jumps in one day. This is Black Monday, right? October 17th or something? 18th. Yeah, October 19th, 1987. So after that, suddenly now, thereafter, Black-Scholes did not explain prices at all. People realize that stock prices are much more fattive. 87. Yeah. And that's when your other guy, Mandelbrot, became more famous. Mandelbrot had looked at cotton prices in 60s and said that they follow fat tail distribution. But nobody cared about that. People just ignored it. They went on with this kind of geometric Gaussian motion model. So completely ignored. He observed data and said.
Like a very rare event it's business model and
And then people realized, okay, we can't ignore these things anymore. Earlier they said, okay, that was a big rare event, yeah. But I'm also making another point that although we knew that prices followed fat tail distribution earlier, we ignored it for a very long time. Mandelbrot had brought this up. This was before his fractal phase.
so this is the same as the complex analysis one, like the matter of
Yeah, no. You should read up on Mandelbrot. He's a fascinating character. Yeah, on all the things that he's done. He brings a fresh perspective on everything. Yeah. Mandelbrot. A great story to childhood, running away from Europe to come to the US. Right. So in any case, so now when you have stock prices which follow a more general process with fat tails, your markets will become incomplete. You will not just be able to trade in the stock price and the risk-free security and replicate options fully.
What is how many?
Yeah, no matter how many things. I mean, you have to kind of play around a lot to kind of, but usually it's an incomplete market. It's maybe you can say if I also allow myself to trade in some vanilla options, and my vanilla options are now following something more than just kind of what my stock price is following. And now with that, I have with that I can replicate more and more exotic options. So for them, it becomes complete. So that's one way people have thought about this stuff. Uh, but in any case, in that world, implied volatility still has a lot of value. It has a lot of intuitive content for people. They have a sense of where the market's moving. I'm not getting time to read up enough on this old stuff. I'll try to, but you should also just read up this stuff on your own. It's kind of, it's more practical stuff. It's
So they one question.
yeah.
So we assumed one security, one risk-free asset.
Hmm.
Again, trying to like analogize the valuable model a bit.
Mhm.
Is there any value in looking at multiple different securities here, or is it that we have that one portfolio hypothesis?
No, so we didn't look at multiple security because we didn't have multivariate Gaussian theorem.
I see.
Now we have that on the next slide. So then slide after that, we'll have multidimensional market model. Okay. Yeah. So we'll do that next time, basically. Okay. But it's good to have a clean theory first under simple assumptions before one kind of talks about. I will tell you, I mean, if I get some chance of doing some extra lectures, some feel for more generally how people go around doing these prices. So I'll have to collect my thoughts a bit.